Hello everyone and welcome again. And today we are going to discuss a new topic, which is uh, transformation of the scattering problem to the laboratory coordinates. So we had already discussed something about what is the scattering in the laboratory system and what is the scattering in the center of mass coordinates. So let us quickly review that again, and then we will continue from there. So if you see that in lab frame, what you have, how the scattering is taking place. So in lab frame, you have your target is stationary at some point, and then the projectile is coming towards uh, that stationary target, and then depending upon the nature of the target and the projectile, this particular projectile is going to get scattered. Okay, so that is in the laboratory coordinate system, where this target is it at rest. Like in Rutherford scattering, you show the alpha particle is moving and this nucleus is at rest. Okay, so and then this is theta is the scattering angle, that this alpha particle is coming towards the stationary target, and then it deviates from its original path. Okay, and then if you draw a asymptote along this, and then you have this angle is your scattering angle. Okay, and then the second thing is uh, it may happen that in the process of this target is get recoil type, and then this target can also get deflected in some other direction. Okay, so if you draw asymptote here, and then it will give you this angle of scattering. It's not a scattering, basically it is the recoil of that target because of so because if this alpha particle is going, and then because of the repulsion is taking place between this and this, then because of that repulsion, this target if it is not very heavy, it's going to get recoil. So this is the vector of vector direction of this particle. Say this is particle 2 and this is particle 1, and this is the vector direction of particle 1 here. So if you draw a relative vector between these two, so between the direction of these two vectors, so then that angle is say this is angle theta, that is going to be the scattering angle in the center of mass frame of reference. Because in the center of mass frame of reference, the particle the center of mass of the two particles which are going to interact with each other, the center of mass of that is this as at the origin of the your reference frame. So a particle is coming from this, so particle 1 is coming from this direction. Okay, and then particle 2 is coming from the opposite direction. Okay, so they are coming opposite to each other, and then they scattered with, and they go to this direction, and this the second particle go to in this direction. So total momentum in center of mass frame is going to be 0, because so these two particles has to go back to back in the center of mass frame. So if you plot, this is going asymptote connecting these two, so this angle is giving you the scattering angle in the center of mass frame of reference. So okay, so this angle is equal to this angle, because in the laboratory frame, if you have the particle is coming, and then because of the recoil is going towards recoiling towards some other direction, then if you draw a relative vector between the vector of uh, these two particles directions, then the angle which it is making with the initial direction, the center of the force line, so that is going to be the same as in the center of mass frame of reference. Okay, so and then what else? In general, the second particle in the laboratory frame is going to be stationary, but whatever the measurement we do experimentally is normally is done for in the laboratory frame of mass system. So now let us try to calculate some kinematics that we are trying to figure out the relation between the scattering angle in center of mass frame and the scattering angle in the laboratory frame. So we're going to have this, if you see that this R1 and V1, this R1 and V1, this is say V1 is shown here in this figure, V1 is here. So V1 are the position and velocity of the scattering of the particle 1. This is 1 after the scattering. Okay, so if a particle is having a mass m and then it is scattered with some target, okay, in the laboratory frame. So then because in the laboratory frame the angle is theta, so you have to be careful about writing this angle. This is different theta and this is different theta. This one theta is this one and another theta is this one. So this is in the lab frame and this is in the center of mass frame. This you have to be careful about. So the V1 is and R1 is the position and the velocity of the particle 1, which is coming towards the target, fixed target, and then it's scattered. Okay, so with the scattering angle theta, and then similarly R1 prime and V1 prime are the position and the velocity vector of the scattering of the same particle in the center of mass. So that is going to be this angle theta. Okay, this angle. So because V1 prime is here and V is here, this angle is a scattering angle in lab frame. Okay, and then we have R and V, that is this is the position vector and the velocity of the center of mass in the lab system. Okay, because in the center of mass system these R is 0, because in the center of mass frame of reference your this center of mass position is at origin, so R is 0 and so its velocity is 0. So this is going to be in the labs frame system. So with the definition we know that this R1 is going to be R upon R1 prime, because you know that if you have two particle, if you have a two particle system, if this is one particle, so this is my particle number 1, its position vector is say R1, and then the second particle is say here, and then and this its position vector is say R2. Okay, and then the center of mass of is somewhere here. This is my center of mass. So if I have for the position vector R, this capital R for this, so these are with respect to this origin O. Okay, with respect to O, and then if I write this R prime, this is R prime, R1 prime, this is the position vector of the particle 1 with respect to the origin set as the center of mass. Okay, so this is so then you can write this if you look into this these three vectors. So this is going to give me the R1 equal to R plus R1 prime. Okay, so this is what I have. Similarly, for you can write for this particle 2, but we are concentrating on particle 1, which is my projectile in case of lab system. So similarly, then we can have V1 velocity and V and V1 prime. So this is evident from this figure, that is this V1 is this vector is going to be this V plus this V1 prime. So this, and this is O, P and A. No, triangle OPA, you see that this is V1 is equal to V plus V1 prime, and these are making an angle theta and theta prime. This is theta and this capital theta respectively, and the vector V is lying in the initial direction from the figure. Okay, because this velocity is center of mass is translational. So also from the figure we can figure it out that this PQ, if you draw a line from this P to Q, this dash line, this one and this one, they are equal. Okay, PQ is AB, but this PQ is in this triangle, that is going to be with this theta is V1 prime, and this is going to be V1 prime sine theta. Okay, this is V1 prime sine theta, and similarly AB is going to be in this triangle if you make this. So this is going to be V1 sine theta. So not let us consider in this triangle. So this is going to be in this one. Okay, this one. So this is going to be V1 and this is this is going to be V1 sine theta. Okay, so this is V1 sine theta and equal to this, because if I take this triangle, then this is again in the center of mass angle, so there is no use of, because we wanted to establish the relation between the scattering angle and center of mass and scattering angle in the lab frame. Okay, so then, and this OB from this point to this point, this OB is basically, this is V1, this whole is because this is my theta, this is going to be V1 cos of V1 of cos theta. So this is V1 cos theta, but this is consisting of the two components, that is one is this one, this is going to be with this V1 prime. So this is V1 prime cos of theta, and then this distance is basically equal to V. So this is V plus V1 prime cos theta. So from here, if I take the ratio of V1 sin theta and V1 cos theta, I'm going to get is tan theta. In this angle is the lap system, and then here I have V1 prime sin theta, and this divided by V and V1 prime cos theta. So on the right hand side I have the angle which is in the center of mass, and the left hand side I have an angle which is in the lab frame. So this is one relation between the center of mass, the scattering angle, and the center of lab frame scattering angle. So you can have V prime, I can have common, so this is divided by V1 prime, and this is again cancelled. So this is one relation, which gives me the connection between the angle, scattering angle, the center of mass frame, and the scattering angle and lab frame in terms of the velocity of the center of mass, and this is going to be the velocity in the center of mass relative to this center of mass frame of reference. So now, since this target is initially stationary in the lab system, this is a lab frame requirement. So the incident velocity which is coming, particle 1, this is m wave coming in the system, is having a v0 velocity such that v velocity. Okay, and this is going to be the same initial relative velocity of the particle, because the target, this is stationary, so there is no relative velocity between this. So whatever the velocity it is having, initial velocity, it is going to be the same relative velocity for that particle. Okay, so then by the conservation of the linear momentum, and you can say that because one is having a center of mass, so m1, this is going to be m1 m2, the two particle center of mass is going to be m1 m2 is equal to m1 v naught square. Okay, whatever the velocity is coming, m1 v naught is equal to the velocity of the center of mass. From here we can find this the velocity of the center of mass is related with m1 v naught upon m1 and m2, and this is this quantity, this is if we divide mu by m2, this is going to be the same, because mu is my m1 m2 upon m1 plus m2. So if I divide mu by m2, so this is going to be m1 m2 divided by m1 plus m2 divided by 1 upon m2. So this will cancel out, I have m1 upon this is m1 m2. So I can write this in terms of the reduced mass, this. So this is one important relation which we are going to use. Okay, mu is in terms of the velocity of the center of mass and the velocity of the particle 1 in terms of particle 2. Okay, now using if we use this relation, in this equation, so I'm going to put in place of v, I'm going to put here this mu v naught upon m naught, so that I can get the relation between v0 and v1 prime. Okay, one in the lab system velocity and the one in the center of mass system. So if I put this tan theta here, in the tan theta, this is, if I put in place of v, this mu v0 and v1, so what I'm going to get is define is a quantity rho, which is here. So if I say, so this is giving me the relation, this is this expression, particular expression, which is giving me the relation between the angle, scattering angle and in lab frame, and the scattering angle in center of mass frame, and the quantity in terms of the velocity ratio, that is of the particle 1 in the lab frame and in the center of mass frame. Now let's try to move further. What other kinematics we can have is also from this. If you concentrate on this angle, this angle A OB, this angle, what I get to get is, this is 90 degree. So I'm going to get is okay. So what is V1 square? I can write this is V1 prime sine theta, and this is so this is V1 square. I can write this V1 square, and then this is this AB is V1 prime, because this is V1 prime sine theta. This angle is theta, so this is V1 prime sine theta square, and then this base is this is V. This is V plus, and this is V1 square cos theta. So V plus V1 square cos theta square. So this h square hypotenuse is length square plus breadth square. This applies. So this V1 sine square theta, and then from V1 prime cos square theta becomes the V1 square sine square theta and sine square theta, and then V square is here, and then this is twice V1 prime V cos theta. So one relation is this we get from here, and the second relation we know that this is V1 cos theta. So V1 cos theta is the whole thing, this. So if you consider this is V1 cos of this theta in terms of cos of this theta in the lab system, this theta. Okay, so this is V1 and this angle is cos theta. So this is equal to V plus V1 cos theta. Okay. So this is another relations. So I'm going to use this relation, this one, so that I can write this cos theta is the whole is divided by the V1, and the V1 I can use from this relation V1 square. So this is going to be under root of this whole, and then I can, if I get what I get, this V, I put V is like we have considered this mu V naught by m naught. So this is going to be mu V naught by m naught, and then similarly we are trying to get rid of the center of mass velocity. So everything has to be in terms of the velocity of the particle 1, either is in the lab frame or in the center of mass frame, and the second thing is the scattering angle in lab frame and center of mass frame. So to get rid of the velocity, the center of mass velocity, you better to remove this with the mu V naught by m naught. This we have already calculated. So if you put here, and then from here inside, from here, if you take here also you put this square of this mu V naught upon m naught square, and then if I take V1 prime common from this here, or this is V1 prime from here, if you take V1 prime square common, so then everything, this V1 comes out, and then this will be V1 prime there, and this V1 prime will be cancelled out with this V1 prime, and here you'll get V1 prime inside here. Okay, so so what I'm going to get is this this V1 prime from here, this was getting cancelled out from here, and this one V1 is going to have here this V1 prime, and from here inside, oh, so this will be like V1 prime square, so this will be divided by V1, so this will come here, and then this becomes 1. Okay, so this is 1, and this comes V1 here, and then V1 square. So you see that this is my quantity rho, this is rho square, and this is also rho. So this is rho, this twice rho, and this is rho square. So this we have already calculated, defined this rho already. Here we have already defined rho. This is ratio of the velocity of the particle 1 in lab frame and the center of mass frame. So now this is lab frame angle, and this is center of mass scattering angle, and then the quantity which is involved here is the velocity of the particle 1 in lab frame and in the center of mass frame. So this is one relation. I have two relation established. That is, one is this cos theta, this which is giving me, and then this is sin tan theta. So this all both the relation gives me the relation between the scattering angle on the right hand side in the center of mass frame, and on the left hand side we have the scattering angle in the lab frame. And then the other quantity which is there is you see is rho, only quantity which is that giving in terms of the ratio of the particle 1 velocity in lab frame and the center of mass frame. Okay. But both of these relations still have this still involves a ratio of a speed through the quantity rho. So now what we can do is that by the definition of the center of mass, because the speed of the particle 1 in the center of mass system can be related to this v prime can be related to the relative velocity of the particle 1 after the collision. Okay, so this is straightforward. We have already established when we started the two body problem related to reduced to one body problem. This we have already calculated is my from here, that I'm not going to calculate it. So, but this is this relation, that is V1 prime is giving you the relation with V, and this is written as in terms of mu divided by m1. So, I am going to use this relation, that is V1 prime is mu by m1 V. Okay. So, this relation, if I replace V1 prime here with this, so I am going to get this in terms of the single velocity particle of the velocity of the particle in the center of mass after the collision. So here I can see that this is, if I replace this V1 prime, so this is I am going to have m1 by m2 because if I okay, what is this? This is mu by m2, and then okay, if I write mu is m1 m2 divided by m1 plus m2, and this is divided by m2. So this is going to be get this m1 upon m1 plus m2, and okay, and if I write m2 m1 plus m2, this is, I don't know why it is m1 by m2. uh, hmm. So the problem is that is how, okay, this is mu upon m1. Okay, so I'm not going to m1, I'm writing m1 upon m2. So the mu is already there. So this is the correction. So mu is already there. So this is what I'm going to put is mu m1 upon v1. Okay, so I'm going to put at v1 prime is mu m1 upon, so v, mu m1 upon v, mu m1 upon v. So this is going to this mu will get to cancel with this. So I have m1 upon m2. Okay, this is correct. Fine, there is no mistake here. So now this is one relation. This rho is clear cut, is in terms of ratio of m1 and m2, and the velocity, relative velocity before and after the collision, okay, of the particle 1. And then if you see that the condition for elastic scattering, if the scattering is elastic, then you know that the total kinetic energy of the two particles remains unaltered. Okay, so then the V is what is after the scattering and before the scattering is going to be same. So this is going to be 1, and then rho is m1 by m2 for elastic collision. So this is important. This is always there, because when the elastic collision is there, so rho we have to get m1 by m2, the mass of the projectile particle and the mass of the target particle. So that has to be taken care for. So this is independent of the energy of the speed, depending upon only the mass of the particle. So this we are going to use to calculate different relation in terms of center of mass and laboratory coordinates. And then second case is if m2 is greater than m1, that is the m2 is the target and m1 is the projectile particle. So if target is very high, then this this rho is this rho is, because this is very high, so almost we divide it is approximately going to be 0. So rho is approximately going to be 0. So if I get one relation which is tan theta, which relates this scattering angle in lab to a scattering angle in center of mass, it becomes, because this is 0, so this is tan theta. So you see that tan theta of angle of scattering in lab system is equal to the tan theta of angle of scattering in the center of mass frame of reference. That means this two scattering angle in the different frames are going to be equal, which is the case for a fixed scattering center. Okay, so then there is no difference that if you're doing the elastic scattering and this if the target is very heavy, so if you do the target is at rest and you do this projectile is coming, m1 is coming, or this m2 is coming and m1 is coming, so there is no difference between the scattering angle. This theta is in scattering in the both the frames, scattering angle is going to be same in case of elastic collision. Okay, so this is all for today, and we will move further from different kinetics and the different relation in lab and center of mass frame of reference. So I think this is done for today. Thank you very much.